Some of the basic trigonometry integral formulas you may have to use while we do combinations of trig functions problems. There are three of them I have listed in the handout. These three you will be using quite often. So it's the way you memorize them is the way to derive it. If you derive something, then it is possible to memorize it better. So we will try to prove integral of tan x dx equal to ln of absolute secant x plus c. So how do we prove it? So let's consider I, which is equal to integral of tan x dx. So we can write tan x as sin x over cosine x dx. Then whenever you have numerator in the denominator, you can just use ordinary substitution method. U sub, I'm going to take cosine x, the denominator, as my u. Then what is du? Negative sin x dx. So this I would become, numerator is sin x dx, that sin x dx would be negative of du. Denominator is just u. So it is negative integral 1 over u du, or it is negative ln of absolute u plus c, or it is ln of absolute u to the negative 1 by property of ln plus c, which is equal to ln of 1 over u, the absolute sign, plus c. So ln of 1 over cosine x plus c, u equal to cosine x. So it is ln of absolute secant x plus c. So integral of tan x equal to ln of absolute secant x. You may be using this later on in problems, so it's better you know how to derive it. Even if you forget, you can actually derive the actual formula itself. Next, let's try to prove integral secant x dx equal to ln of secant x plus tan x plus c. We will prove that. Integral of secant x whenever you're proving something, then you have to work on only one of the sides and arrive at the other side. So let's start with the secant x. The integrand is secant x. So secant x, we have no rule. We can only maximum write that as 1 over cosine x. But that doesn't help us because we don't have, if we take 1 over cosine x and write cosine x as u, we don't have a sign on the numerator, so that is not going to work. So the way we do this one, so we write secant x as secant x times 1. Then that's 1 can be written as anything divided by itself. So 5 over 5 is 1, x over x is 1. So I'm going to multiply and divide by the same quantity. The quantity that I'm going to multiply and divide is secant x plus tan x, the clue that I'm getting from what I need on the right hand side. So multiply and divide by secant x plus tan x. Now, you distribute the numerator, which is secant square x plus secant x tan x divided by secant x plus tan x. So this is just secant x. So we are writing secant x in a different way. Now you integrate both sides. So when you integrate both sides, I have a numerator in the denominator. So the best choice for you, the u sub method is what I'm using. So use secant x plus tan x, the denominator. So du, which is the derivative, which is secant x tan x, which is actually the derivative of secant x, derivative of tan x, which is secant square x. So I, which is equal to integral secant x dx, which we wrote as this expression over here, which is secant x tan x plus secant square x. I'm just switching these two terms, dx, divided by secant x plus tan x. This integral secant x plus tan x equal to u. So substitute that u. If you look at the numerator though, secant x tan x plus secant square x, the whole thing dx is secant x tan x plus secant square x, the whole thing dx, that is nothing but du. So the numerator whole thing is just du. So it is now integral 1 over u du, which is ln of absolute u plus a constant. This ln of absolute secant x plus tan x plus constant. So integral of secant x is ln of secant x plus tan x plus c. Sometimes you rationalize, sometimes you take the common factor. So these are some of the techniques you would use. So here, by looking at what answer we need on the right hand side, we kind of guessed what we need to multiply and divide by, which gave the answer for us. I would like you to try the next formula, which is exactly similar to the one that we did on secant x. So cosecant x you need on the right hand side, cosecant x minus cotangent x in the formula. So when you try this on your own, what you may want to do is to write cosecant x as cosecant x times 1. Then you write the cosecant x, then you write the 1 as cosecant x minus cotangent x divided by cosecant x minus cotangent x. So you try that way. You can easily prove that. So for this third one, to prove cosecant x dx equal to ln of cosecant x minus cotangent x dx. So you can try this one on your own. The cosecant x can be written as cosecant x times 1. Then cosecant x, that 1 can be written as something divided by the same thing. For that, the hint is this part, multiply cosecant x minus cotangent x divided by cosecant x minus cotangent x. Okay. I think you would be able to try this way and then arrive at the integral value equal to ln of cosecant x minus cotangent x plus c. Let's try evaluate integral cosecant cube x dx, which is, you see, it is not combinations of trig functions, but we notice that the exponent of cosine is odd. So I want to write this as cosine cube x as, because whenever you have an odd exponent, you want to save one of them. So save one of the cosine. So there are three of them. So write cosine square x times cosine x. And this is the one you are saving. If you are saving cosine, your substitution should be usually the other trig function, or you can assume this to be kind of antiderivative. You don't have to worry about the sign, but I mean plus or minus, but kind of antiderivative would be the best choice for you. So du would be cosine x dx. Then what Pythagorean identity we are going to use? Cosine square equal to 1 minus sine square. That is the Pythagorean identity we are going to use. So it is 1 minus sine square times cosine x dx. It is 1 minus u square. Cosine x dx is du after all. So on integration, this becomes u minus u cube over 3 plus a constant. So what is u? U is sine x. So sine x minus sine cube x over 3 plus a constant. Next, let's try example 2. Find integral sine to the power 5x cosine square x dx. So anytime you have sine cosine combination, you have to see which one has an odd exponent, and anything with the odd exponent must be saved, right? Odd must be saved. That means one of the sign should be saved. So let's write I as integral sine to the power 5x cosine square x dx. We are saving a sign. That means u should be cosine x. So what is du? Negative sine x dx. Then we are going to use the Pythagorean identity sine square x equal to 1 minus cosine square x. So it is integral. So cosine square is u square. Then we are going to save a sign. So because out of the 5 we are saving one sign, we write like that. This is the one which is getting saved. So sine to the power 5 is written sine to the power 4 times sine. Then for cosine square, anyway, that is just u square. So let's keep it as cosine square only. Right? So here, again, this, because we are going to use sine square equal to 1 minus cosine square, then this sine to the power 4 is sine square, the whole square, right? So you're going to write that as 1 minus cosine square in the place of sine square, the whole square, right? Sine square is 1 minus cosine square. So leave the cosine square as cosine square. Then leave the sine x dx as is for now. Now let's apply u. So it is 1 minus u square, the whole square. Cosine square, that is u square. And sine x dx is negative du. So now we can expand this, which is 1 minus 2u squared plus u to the power 4 times u squared with a negative sign out du, which will be negative integral. If you distribute the u square, it's u squared minus 2u to the power 4 plus u to the power 6 du. Expanding that, you get negative u cube over 3, taking the integration, taking the integral of these, so minus 2 to the power 5 over 5 plus u to the 7 over 7 plus an arbitrary constant. So u should be written back with the original variable. We have taken u equal to cosine x. It's negative cosine cube x over 3 minus 2 fifth cosine to the power 5x plus cosine to the power 7x over 7 plus additive constant. Next example is find integral secant cube x dx. We notice that secant function is appearing as an independent function here. It is not along with tan. So we have to apply a different technique here. So either you must, right now you know only some of the trig combinations and integration by parts and then regular use up method. So we will have to see which one works here. So we know one thing for sure that derivative of tan x is secant square x. So we will write secant cube as secant x times secant square x dx. We'll write like this. Then we will apply integration by parts. So u equal to secant x, and then we will take dv equal to secant square x dx. So we are going to take u equal to secant x. So du is secant x tan x dx. Then dv is secant square x dx. So v is integral of secant square x, which is equal to tan x. So I is written as integral u dv. So it is uv minus integral v du. So uv, that is secant x tan x minus integral v, which is tan x du, which is all of this secant x tan x dx. So now I, which is secant cube x dx, becomes secant x tan x minus integral. We have a tan and we have tan here, so that becomes tan square x secant x dx. The tan square can be written by Pythagorean identity. Tan square x can be written as secant square x minus 1. This is another identity, Pythagorean identity, one of the variations that we saw earlier. So this tan square, I'm going to write a secant square minus 1. Then I'm going to keep the secant x as is. So I, which is integral secant cube x dx, equal to secant x tan x minus, if you distribute, it is secant cube, and you have a minus sign outside. Then if you distribute, it is minus secant, but there is a minus sign outside. So it is integral secant x dx. If I distribute and split the integral, and then also taking into account of the minus sign that you see outside the integral sign. You're distributing along with the minus. If you notice, this integral that you have seen here is exactly the same as the integral that you started off with. So we will write this integral I as secant x tan x minus again I plus integral secant x, which we derived earlier. What is integral secant x? Integral secant x from what we actually derived is ln of absolute secant x plus tan x. Actually derived that one. So we are going to substitute that. Of course, we have to write the c, but the c can be added at the end of the problem. Now I'm going to move this I to the left-hand side, negative I to the left-hand side. So that will get added now. I plus I equal to secant x tan x plus ln of absolute secant x plus tan x. If I divide the whole thing, so this is equal to 2I. So 2I equal to that. So if you just isolate I, or you have to divide the entire thing by 2, that will become half of secant x plus tan x plus ln of absolute secant x plus tan x plus the additive constant, arbitrary constant that we add usually for indefinite integral. So you have learned several techniques now how to combine the trig functions, and sometimes you have to look at the odd exponent and the even exponent and then save the appropriate trig function, or sometimes you have to use a different technique uh, such as integration by parts. If you notice in many problems that we have seen in these videos, that we have actually used a lot of Pythagorean identities as well. So in the suggested problems, I have done some problems in my videos. Um, One of them might be where you have cotangent and cosecant combination also along with the other one. So this section needs a lot of practice. So try them, understand the method. Hope these videos help.